Welcome back. So, we were discussing the three-phase power measurement techniques. We covered the lecture part where we have discussed how, for a balanced system, 2-watt meters will be sufficient to measure the three-phase power. And when the power factor is completely varying, then in that case, it is better to go with 3-wattmeter method. We will see some of the problems to understand the theory that we have studied. Let us see the problem number 1. So, in the given circuit, we have to obtain the total power which is absorbed. When we say absorbed, meaning is we are basically trying to find the real power, because it is only the real power which can be absorbed. So, reactive power and apparent power, they are not being computed when the term absorbed is used, because power can be absorbed or dissipated in the resistor only with the power loss being given as I square R. So let us focus on this particular problem. So we have a three-phase load. Now, if we observe the three-phase load, in the first phase we have 15 ohm resistor. In the second phase we have combination of RC load, and in the third phase we have a combination of RL load. If we observed the impedance of the first phase, impedance of the second phase, and impedance of the third phase are different, so it means that the system is unbalanced. Now, the voltages VAN, VBN and VCN, these are the phase voltage, because we are measuring the voltage with respect to the neutral point. So these voltages are given to us. Similarly, the current IA, IB and IC, which are flowing in the individual phases, are also given to us. These may have been computed with some other part of the problem which is there on the left hand side, and these voltages and current may have been computed. So we are considering that these data are known to us. If you remember, we have already discussed this problem in the previous tutorial problems in one of the three-phase circuit where we have computed this data. So we are considering this to be the known data, and we will be estimating the total power which is absorbed in the network. We have seen from the theory that the real power is nothing but the real part of the complex power S, where the complex power S is nothing but VI conjugate. So here, when we talk about the single phase power P1, single phase power P2 and single phase power P3, we are going to take the phase voltage and the phase current. So the real part of VAN into IA conjugate will give me P1. The real part of VBN into IB conjugate will give me P2, and real part of VCN into IC conjugate will give me P3. We also know that the power formula P is nothing but VI cos of phi, where phi is the phase angle between voltage and the current. So here we are using VIAN IA into cos of theta VAN minus theta IA. So this is the phase angle between the voltage and the current. Similarly, we are using the phase difference of the other voltages and current in the corresponding phase 2 and corresponding phase 3, where the voltages are VBN and VCN, currents are IB and IC. So we can easily estimate this power P1 is 667 watt, power P2 is 800 watt, and power P3 is 600 watt after substituting the values of the voltage, current and the power factor angle in the respective phases. It means that the total power is nothing but the sum of the power P1 plus P2 plus P3 in the individual phases, as the load is unbalanced. So here, since the load is unbalanced, so we are adding the power in the individual phases. If the load is balanced, we could have easily multiplied this with 3 times P1, because in that case your P1 will be equal to P2 will be equal to P3. This is for the balanced system. However, since we are dealing with the unbalanced system, the total power, which is sum of all the powers in individual phases is giving me 2067 watt. So this is the power. Now we can easily validate that this power, whatever we have estimated, is correct, because the current IA, IB and IC are given to us, and the corresponding resistance of the phase A, resistance of the phase B and the resistance of the phase C are known to us. And we know that the real power P is nothing but I square R. So we are putting a summation in all the three phases. So we can estimate that the total power, again we are getting 2067 watt, which is similar to what we have got by the 3-wattmeter method. So if the current and the values of the resistances are given, we can easily estimate from this point where the power is I square R. If the voltage and the current are mentioned, then we can estimate by the 3-wattmeter method. Next problem. Now we have to use the 2-wattmeter method, where the readings of the wattmeter are given. P1 is 1560 watt and P2 is 2100 watt. These are the power measurement, the real power by the 2 wattmeters. Now the load is basically connected in the form of delta, and the line voltage is given 220 volt. We have to obtain 4 quantities. What is the per phase average power? Average power means real power. What is per phase reactive power? The power factor and the phase impedance connected in individual phases. So we know that in 2-wattmeter method, the total power is nothing but the sum of the 2 wattmeter readings. So 3-phase power is P1 plus P2. These readings are already given to us. So the total power is 3660 watt. Since the system is balanced, the per phase real power will be 1/3 of the total average power. So that is 1220 watt. Similarly, the total reactive power we can estimate using the formula √3 P2 minus P1, where P2 is more than P1, and we are getting 935.3 volt ampere reactive. And this is for the 3-phase reactive power. So per phase reactive power again will be 1/3 of the total reactive power, which is equal to 311.77 volt ampere react. Now we can easily estimate theta, which is the angle between the voltage and the current, is tan inverse of the imaginary part by the real part. So imaginary part is the reactive power, which is 3-phase, and the real part is basically the real power. So it gives 14.33 degrees. So this is power factor angle, and hence the power factor we can obtain 0.9689 cos theta. This will be lagging in nature. We have to estimate the per phase current, which we can obtain from the per phase power formula. So power is VI cos phi. We can estimate the current by rearranging this equation, where the power we have computed per phase power is 1220 watt, and the voltage 220 volt is the line voltage, which is equal to the phase voltage because it is a delta connected load. So we have 220 volt. Now cos theta, which is the power factor, we have got 0.9689. So the current we are getting 5.723 ampere. We have to obtain the impedance. So per phase impedance is per phase voltage by per phase current. So per phase voltage is 220 volt and per phase current is 5.723 ampere. Once we divide it, we get 38.44 ohms. So this is basically the magnitude that we are getting. What about the angle? So angle will come from here. So we are able to write the complex impedance per phase is 38.44, which is the magnitude, and angle 40.33. So this is the per phase impedance. Next problem, problem number 3. So we have balanced load, and the load is 3-phase in nature. The per phase impedance is given to be 8 plus J6 ohms. If the load is connected to a 208 volt lines, predict the reading of the wattmeter W1 and W2. So 2-watt meters are there, W1 and W2. We have to find their readings. The per phase impedance of the load is given and the supply voltage is given 208 volt. And also determine the real power and the reactive power of the three-phase system. So the impedance per phase is basically 8 plus J6, which is in polar coordinate we have the magnitude 10 and angle 36.87. So the power factor angle is 36.87, which will come from the impedance angle. And the line voltage or the supply voltage is 208 volt. It means the line current is nothing but the voltage divided by the magnitude of the impedance, which is equal to 10, and the voltage is given in line, so we have to obtain in phase. So phase voltage is nothing but the line voltage by root 3. So we have to divide with root 3, we get 208 by root 3, and the magnitude of the impedance is 10, so we get 12 ampere as the line current. So this is basically the magnitude of the line current. 2-watt-meter will measure the power P1 and P2, and the magnitude will be VL, IL, and the angle will be cos theta plus 30 and cos theta minus 30. So this we have discussed in the lecture discussion where the derivation we have seen and the important formulas also we have seen regarding the real power and the reactive power. So this is the real power formula. We have the VLIL as the magnitude, and one phase will measure the power 30 theta plus 30, another will measure theta minus 30. So once we substitute this voltage and the current and the power factor angle, we get the power as 980.48 watt and 2478.1 watt. So these are the powers which are associated with P1 and P2 watt meters. So wattmeter 1 will read the readings 980.48 and wattmeter 2 will read 2478.1 watt, which was the first part of the problem. Note here, the power P2 is greater than P1, so that indicates the inductive load because the reactive power will be greater than 0. We have seen this in lecture class. So this is evident also from the load. If you see the load theta, that is positive quantity, which indicates that the load is inductive in nature. Finally, we can obtain the real power and the reactive power. So real power is nothing but the sum of P1 plus P2, that is the real power of wattmeter 1 and wattmeter 2. We get 3.459 kilowatt, and the reactive power is root 3 times P2 minus P1, so that gives 2.594 kVAr. So we are able to estimate the real power and the reactive power using 2-wattmeter method. If we require to determine the apparent power, that will be under root of PT square, real power plus QT square. And power factor also we can estimate from 10 theta, which we have done it. So these three problems we have discussed on three-phase power measurement using 2-wattmeter method and 3-wattmeter method. And this will clear the concept regarding the power measurement techniques. Thank you for now.